I apologise for having to make a video like this, but I wanted to respond to Mr. Strange's video. Well, the embarrassment comes from the fact that I'm having to explain what is the bleeding obvious, really, and you just sort of feel a little bit silly having to do that, but if you have to do it, you have to do it. Now, I must apologise for the quality of the video. It's probably not the best. The only microphone I have is the one that's built into my laptop, and so it does go up and down in volume a little bit, and there may be a little bit of clunkiness within it, but it's the best I can do at short notice, and I don't want to spend a great deal of time on it, so I've done it and it's all put together. There was no script, so there are a few ers and ums along the way, but I hope you forgive that because it explains all of the rubbish within Strange's video. Here you go. The Hasselblad camera that was used on the moon landings. It's a lovely little device, isn't it? But what I want to show you here, this is on a website called Digital Rev, and I'll show the URL in a moment. But the thing to notice here that there was a couple of cameras used. One here was the intra-vehicular camera, but note it had an f2.8 8mm lens. That's the important bit for that camera. But it wasn't the one used on the lunar surface. The one used on the lunar surface is the EVA camera. And it had an f5.6 60mm lens, which is important. We'll need this information later on. 60mm focal length. Remember. I'll have a quick look at this lens for you. There you go. Notice there's two controls on the lens. There's one at the back here, it's all the way around, that adjusts the focus, the focal point set to infinity on this device, and this one here which sets the aperture. And as we've been told, and it's actually written on the lens there, the widest aperture here is f5.6. Don't know, I've not found out what the smallest aperture is, but it could easily be something as wide as f22, maybe even smaller. Here we're on a website called photographylife.com, and if you look at the top of the URL, I'm in an area that's explaining what is lens compression. Looking at the first photograph, there's a young lady in the foreground. In the background, notice this Canadian flag and its pole. Also look at these flower pots. This was taken using a 24 to 70mm focal length lens that was at the wide end, set to 24mm. The next image shows the same young lady at the same scale. Look what's happened here. The flower pots, they've compressed, they've come forwards, they're much larger than they were before, as is the flagpole. But the young lady is very much the same size as she was before. Note that the second photograph here was taken at the 70mm end of the same lens. What happens if we increase our focal length again? Here, let's have a look. We're using an 80 to 400mm lens set to 105mm focal length. And lo and behold, the flagpole has come closer. The flower pots have come closer. This is lens compression. Again, we're midway here, 200mm focal point. The flower pots have come really close. So close, in fact, that to keep the young lady in roughly the same sort of scale, the flagpole can't even fit in the field of view. It's well off to the right over here somewhere. And going one step further, at 300mm focal length, look, this is huge now, this flower pot. And right over there somewhere will be the flagpole. There's the moon, boyo. There should be a moon. Sorry, Taffy. There isn't a moon in this photograph. But can you see what's happening? Those things in the background, like the moon, are moving closer. No, 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 boyo. It's NASA moving those flower pots forwards. Okay, Taffy. Just for you, let's look at the same stuff with a round object. Not quite the moon, but round. We only have to look at the vertical, and well, let's look in this far right-hand column. Notice here the orange is in front of a very big house. The house is massive in comparison to the orange. As we go down here, we keep the orange approximately the same size. But look what happens to the house in the background as we go down from, I believe it says there, let's say 400, I can't read that properly, 400mm lens all the way down to a 20mm at the bottom. So this has got a wide angle, very wide angle. Let's change the colour for you so you can see what I'm drawing. Very wide angle here, very narrow angle up here. And we'll look at that again a bit later for you. But you can see how just by changing the focal length, the background is drawn closer or pushed further away. But you can keep the foreground much the same. No, this is all wrong. This is all wrong. That's an orange, not the moon. That's an orange. It won't work with the moon. Sorry, Strange. This is physics. Ask Taffy, he knows all about physics. Okay, here we are for you, Taffy. Pictures of the moon. What I want you to notice here is that the small image of the moon is on a 200mm focal length, and the large image of the moon is on a 2000mm lens. Note the difference in blue, where the 200 is written down as 135 and the 2000 is written down as 1500. I'll show you that on the next slide, so why that's the case. But notice, depending upon how you have your camera set and what your lens is and what your focal length is, the size of the moon will change from absolutely minute to absolutely massive. And as we saw in the previous set of images with the young lady in, the foreground set the same, changing the focal length, it brings the background forwards. Okay, so here we are looking at a table, a field of view against focal length. Now the field of view, if you look at that column, you've got in the row with 40mm there, 98 degrees by 147 for a 35mm frame camera. That means it's showing you an angle horizontally of 147 degrees and vertically of 98 degrees, and that's common with the aspect ratio of photographs. The small photographs you maybe wear a 10 by 15, and that's the typical aspect ratio that comes from a 35mm film camera. Looking at the next column along, the field of view for a digital camera is actually slightly less, and that's primarily because the sensor in a typical digital camera is smaller than the 35mm camera. It's about 2/3 the size, and that's primarily again because it's cheaper to build smaller sensors. It is possible to buy full frame 35mm digital cameras, but they are very, very expensive devices. So most modern digital cameras are smaller than 35mm, and down to your phone cameras, which are actually minute sensors. But you'll see that in another slide I have on sensors. But looking at this, you can see that the size of the moon that you would get varies with focal length. So millimeters, where you'd have a 0.2 millimeter moon on your image, all the way down to 2000 millimeters, where the size of the moon on your sensor would be 18.4 millimeters. Now that's a range of 90 times difference in the size of the moon, dependent upon the size of your focal length. Now let's look at the camera sensors. The normal size that we refer to is full frame 35mm for standard type cameras. These are not large format cameras, but they are the standard ones that you would normally put 35mm film in the olden days. They have a size of 36 by 24mm, which is shown there. Digital cameras, on the other hand, have a smaller sensor size, and you can see here this one represents the sensor size of a Nikon and Sony in relation to the full frame. This shows the Canon in relation to the full frame, etc. And right at the bottom you have a small sensor which is used in very small cameras, and your mobile phone camera may even have a sensor much smaller than that. The problem with a sensor of this size is that your focal length calculations and your image have to be converted into equivalent focal lengths for a full size sensor for us to be able to compare them. Now, given that the photographs that Strange used in his video are all randomly chosen off the internet, there is no information provided as to what the focal length was, what the camera was, what the sensor size was. So without that information, it's not possible to actually compare two images with each other. You must also remember that the objective of people on that night when the moon was closer to the Earth than normal and huge was people were taking photographs of the moon. So the adjustments they made on their cameras were to photograph the moon. So it's not surprising that they would have adjusted so that the field of view brought the moon to be the primary and huge within the photograph, the primary image. Here we have a few photographs taken on the moon, except for the odd one like this. All I've done is search for some Apollo photographs on the internet to see what came up. As we've discovered before, the Hasselblad camera used on the moon had a focal length of 60mm. In the command module they did have a Hasselblad with a longer focal length that would have permitted different types of shots to be taken out of the command module windows. So they were able to sort of zoom in and out on a few things, which would have given them a little bit more creativity around the photography that they made. But on the moon, the 60mm lens makes quite a lot of sense, having looked at all the stuff we've looked at so far. It does give you a reasonably good wide field of view. And when an astronaut is using a camera without a viewfinder, having a wide field of view does mean it doesn't need to be too accurate in the direction he's pointing it, because with that wide field of view he will get a reasonable photograph. So if you're looking at these images, all taken with that type of camera, a few exceptions. If you look there and look there, let's forget those ones. They're not from the surface. So there you go. You can see that on the moon their decision was actually really quite good, with sort of the encumbrance of their gloves, etc. Zero viewfinder, a nice wide angle lens would allow them, using a full frame camera. I believe these Hasselblads are full frame, so that's even bigger, a bigger piece of film than a 35mm, possibly 70mm, twice the size, may even have been bigger. But that would have given them the ability to take photographs on the moon without having to worry too much about accurate framing. You were able to catch nice shots, and you can trim them down afterwards. You can crop them. Most photography these days is taken and cropped. Clearly it's better to crop in camera, and most professional photographers will do that, and what all that means is you frame the shot as you want it to be, but without a viewfinder, not possible. So inevitably there would be a need for some cropping. Actually, that one shouldn't be there either. But as I say, these were just random photographs kicked up by a Google search. Whilst we're talking of Google searches, it's amazing what it kicks up. I actually found this image of Taffy himself doing some analysis of Apollo photographs on his laptop. Well, I think we've covered the size of the moon, size of the Earth issue just by giving some basic information about photography and physics that the boys themselves, Strange and Taffy, could easily have done themselves the research by a little bit of Googling. Now I want to look at this image, and we are told by Strange, and we're supposed to believe everything he says, that we have the moon surface here, clearly visible, a nice picture of the Earth, and another picture of the moon. Well, I would love to see a higher resolution image than the one provided here. You note that what Strange does is he gives you a very small sample of one photograph and a small sample of another photograph, so you really don't get a good view of these, and that's probably deliberate. But I suspect this is an internal reflection in the lens of this. And what's an internal reflection, you may ask? Well, let's have a look at that for you. We're presented here with a diagram of a very simple lens. It's got multiple layers of glass within it. There's only 3 shown here. Most modern lenses have significantly more than this. One of the lenses in my camera has something like 13 pieces of glass within it. So internal reflections are not uncommon, but readily recognizable, and most photographers would recognize them immediately. Here we have a bright object. They've called that the sun in this one. As you can see here, the sun image goes straight through and goes onto the camera sensor here. But off this surface here, there's shown an additional reflection which shows a path there. Now these lenses are coated. There's a anti-reflective coating. And that's designed to reduce to the minimum internal reflections. But they're almost impossible to get rid of totally. But what it does mean is that this image that goes here and reflected from here is attenuated. It loses some of its power here and it loses some of its power here, but it should be transmitted fairly well through the rest of it. So what you actually get is a secondary image. You notice it's not in line with the first. You get a secondary image which is much less bright, and that's important. There's a nice example here to show you. What we have is a flashlight, and it's in there somewhere, but it's far too bright for this camera to handle. So you can see we get all this flaring effect and this washout here, totally washed out. But it has created internal reflections. So bouncing around within the camera has resulted in this image here appearing. Actually, you can see that's a flashlight. You can see the bulb in the middle and the reflector on the outside. So bright objects, so it doesn't need to be the sun, any bright objects, and in space the bright objects are the sun and the reflective planet Earth and the reflective moon. They're giving incredible amounts of light and therefore likely to be producing reflections. Bugger me, Taffy, what you thinking? What you thinking? La 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 la. I thought that was brilliant. Strange, but it looks like we bollocksed up here a bit, boyo.